Hello. In part two of our section on systems of difference equations, we're going to return to the question we first mentioned about the predator-prey relationship of an Italian fishing village. So in that village, they caught both sharks and skates. Skates is a type of fish. That's the prey. Sharks are the predators. And in a way, the fishermen are predators as well. And one thing they noticed is that the proportion of predators versus prey varied over time. And so we're going to analyze this predator-prey relationship in general, and then we'll play around with some specific numbers and see what happens. So let's let S sub n equal the number of sharks or predators after n, and we'll use the term season generally. That could be a year or a week. We won't worry about the actual time period. And then we'll let F sub n equal the number of fish, which are the prey, also after n seasons. And as we might expect, the number of fish presumably are going to grow if there aren't sharks around, and the number of sharks would die off if there aren't fish around. So we can model that with a difference equation. So the change in sharks, we expect to go down. So I'm going to write a proportionality like that, minus d times S sub n. And the change in fish, we expect to go up, so I'll call that R times F sub n. And notice I'm assuming that D and R are greater than 0 when we do this. Now, we're not quite done because somehow we have to take into account the interaction between the two because that makes a difference. So we need some sort of mathematical way of describing the situation where if I have a lot of sharks and a lot of fish, then that's going to be a lot of interaction. So there's going to be a lot of sharks eating fish, presumably. And if there is not very many of any, then of course there'll be less interaction. And something in between if there's a lot of one and less of the other. So if you think about mathematically what that might look like, you might get more than one answer. But our solution is going to actually go back to Latka and Volterra, who in the 20s independently came up with this model. And it may remind you of the logistic model that we saw briefly in the previous section, and that's to multiply. So what we're going to do is we're going to add a term here, alpha times S sub n, F sub n, and then minus beta, S sub n, F sub n. And once again, alpha and beta are also positive because we're using the signs in front to indicate what we expect to happen. So the more interaction there is, we expect that to be good for the sharks because they're the predator. And so that alpha is going to have a positive coefficient and beta is going to be negative coefficient because, of course, it's not good for the fish. And then, of course, we also need some sort of initial value for F0 and S0, the sharks and the fish. So this is our initial model. Okay, so notice we made some assumptions here about interaction that we've expressed mathematically, and we're continuing the proportionality argument. This is a pretty simple model, but the nice thing is that it can give us some insight even if it's not perfect in considering all the things that could affect the number of fish or sharks in a body of water. So let's look at long-term behavior. So we did this in our last example, and as you'll recall, the key is to take the limit of both sides and give those limits to the shark and the fish a name like, say, S and F. So I'm going to say the limit as n goes to infinity of S sub n is equal to S, and the limit as n goes to infinity of F sub n is equal to F. And then we'll take the limits of both these equations. So take limits. And so notice what do we get? So notice the change in S sub n. Well, that's going to be basically S sub n plus 1 minus S sub n. So that's 0, okay, is equal to minus ds plus alpha SF. The change in F sub n, well, remember that's F sub n plus 1 minus F. In limit, that's also going to be 0. And then we have R times F plus, minus beta SF. And so now we want to solve for S and F. Well, this first equation has an S in every term, so I can divide by S to get 0 equals minus D plus alpha F. So to divide by S, I'm assuming S is not 0. And likewise, if I do the same thing in the next equation, divide by F, then I'm getting 0 equals R minus beta S, where I'm assuming F is not 0. So these two conditions actually give us an equilibrium of 0, 0. Which is not a surprise. If I have 0 sharks and 0 fish, then that's never going to change, and so it's going to remain 0 indefinitely. So it's nice that we get that equilibrium, but that's not the one we really care about. The more interesting one is if we solve this equation, which now, notice, is not too bad. Move the d over, divide by alpha, so we get F equals d over alpha, and this, we get S equals minus R over minus beta, or R over beta. So we get an equilibrium of, in this case, the S is first, so we'll use S first as here as well, R over beta, D over alpha. So we get two equilibria. And so now we just need to decide what does that mean in terms of actual numbers. So let's go to Excel and see what this looks like. But before we do that, let me give you a few numbers to actually play around. And if you want to try this first on your own, now that you've seen some spreadsheet work, you can see what you get. D equals 0.2. R equals, how about 0.3? Alpha equals 0.002. And beta equals 0.001. And these numbers are just to give us a practice. They don't necessarily have to do with a particular species, but it gives us a chance to practice. So let's look at the spreadsheet after you've had a chance to practice on your own. So here's our spreadsheet. So we have our seasons going from 0 to 60 or so. That'll be enough to give us some good data. And we need to have a certain amount of predators and prey. And so let's see what we get in terms of an equilibrium here. So we said D was 0.2, R was 0.3, alpha is 0.002, and beta is 0.001. And so our equilibrium, S, should be R divided by beta, and F should be D divided by alpha. So we get 300 and 100 is the sweet spot supposedly for these animals. And so now we can type in our equation. So our equation, remember, is the previous term plus our formula for the change. And our change, we said, was minus D times the previous number of predators plus alpha times previous number of predators times previous number of prey. That's a good sign. Did it change? 300, that's what we would expect. And then we'll do the same thing for our prey. R times the prey minus beta times the predator times the prey. So it looks promising, but remember we need to put some dollar signs here for all of our constants. The parameters for the model, which would be E2 and E4. And likewise over here, E3 and E5. Drag that down, Trilling equilibrium. And we can insert a chart to see what this looks like. And so nothing too surprising so far. So we see an equilibrium. Our question might be, is this a stable equilibrium? So if I change this, what happens? So for example, let's since 400 is kind of the total number of animals in this, let's make the fish 400 minus whatever we put in for the predator. So for example, if we made this, say, 310, notice we're getting something quite a bit different. All right, so only 2 more sharks and 10 more sharks, 10 less fish is changing things. And if we go the other direction, likewise, we're getting more and more oscillation, not less. So different than what we've seen before. What if we try 275? So notice in this case, we're getting some large oscillation towards the end, but it appears that at least both, at least after 60 seasons, both are doing fine, right? So it's going back and forth, but both are doing fine. But what happens if I have less sharks? So you would think less sharks would be better for the fish, but if I go down to 210, then notice then after just 35 seasons, the fish are extinct, which of course means the shark will be as well. So an interesting feature is that fewer sharks actually causes a quicker demise of the fish, which seems a little bit counterintuitive. So you can play around with this more. You can see what happens for more or less. And of course, we don't have to have 400. We could see what if I had 300 of each. Okay, notice that also ends in some interesting numbers here. We eventually get a negative. One thing we need to be aware of that Excel is not going to catch is if we start getting negative numbers, then the model is done. Certainly any values past that are not going to be valid anymore. So you do have to be careful about that. So just to summarize then, this modeling process, sometimes we like fitting a model to a data and getting a nice fit to the data, but sometimes we can just get some observations that may be as valuable as actually fitting a model to data. And so here's 3 observations that are worth taking away from this particular exercise. First of all, oscillation is expected or can be expected. Now, we're not guaranteed that our model is correct, but this is just what our particular model predicts. And so if we observe this in nature, then we can say that perhaps our model has some validity to it. And sure enough, if you look, there are predator-prey relationships in nature that do exhibit an oscillatory nature. As we already discussed, a decrease in predators may not always benefit the long-term survival of the prey. And that fishing village example seems to be a potential example of that. And then a third thing is that a small change in population can have a dramatic effect on long-term survival for predator and or prey. And so I believe all 3 of these things have been observed in nature. So the Lock-Volterra model is a nice model, even though it's pretty basic. It still can teach us some things, and then we can get more sophisticated as needed. So that's it for this section. We'll see you in the next video.